Good afternoon, my name is Ekaterina Didenkulova, and today I would like to present you the work Non-integrable Soliton Turbulence within the Schamel equation, made with co-authors Marcelo Flammarion and Yefim Pelinovsky. As is very well known, solitons are particle-like waves that retain their shape when moving and do not dissipate when interacting with each other. They are able to transfer energy over long distance and play a significant role in the wave dynamics. They exist in ocean and atmosphere, plasma, optical waveguides, and etc. When there is a large number of solitons with random parameters, we can talk about the so-called soliton turbulence or soliton gas. The property of solitons to interact elastically with each other gives rise to an obvious association with the gas of elastically colliding particles. Usually this term is used for integrable models such as nonlinear Schrödinger equation and Korteweg-de Vries equation. And in the last 10 years, the development of the theory of integrable turbulence has been widely developed both theoretically and numerically. And here you can see just some references, but the list is of course much bigger. The problem of soliton turbulence may also be investigated in non-integrable models, allowing the existence of soliton-like impulses which interact almost elastically. However, the analytical methods used to study the integrable turbulence are not applicable here, and only numerical simulation can be applied. So we study the soliton turbulence within the non-integrable Schamel equation, which describes ion acoustic waves, nonlinear wave dynamics of cylindrical shells, and longitudinal waves in the walls of annular channel. It contains a modular nonlinear term with non-integer power and has the following soliton solution. This equation also possesses the following invariants, which remain constant throughout the evolution of the wave systems. So they are the mass, the momentum, and the Hamiltonian. Due to the fact that solitons in non-integrable systems interact inelastically, two effects arise as a result of their collisions. The first one is associated with the radiation of dispersive tails, which should lead to the formation of a gas of quasi-sinusoidal waves interacting with the soliton gas, so mixed turbulence. And the second effect is associated with the non-recovery of the amplitudes of interacting solitons and the energy transition from a small soliton to a large one. In the presence of a large number of solitons, this should lead to the formation of an abnormally large soliton, so-called rogue wave. These features distinguish non-integrable soliton turbulence from integrable turbulence and, of course, should be studied. So let us first investigate the collisions between two unipolar solitons, solitons with the same polarity, in the context of the Schamel equation. To do this, we will compare the numerical results with known classification of the characteristics of two solitary wave interactions in the integrable KdV equation, based on the ratio of the initial amplitudes A1 and A2. So there are three types of interaction following this classification. They are exchange for such a ratio of amplitudes, overtake interactions when A1 to A2 is bigger than 3, and also the third type of interaction, it's transition for such amplitude ratio. So we consider two solitary waves S1 and S2 with amplitudes A1 and A2. Initially, the solitary waves are located at a considerable distance from each other, ensuring that there is a significant separation between them. First, let us take A1 equal to 1 and A2 equal to 1.8 which corresponds to exchange interaction from the previous slide. So two solitary waves exhibit nearly identical shapes following the collision. However, it should be emphasized that this is not an exact two solitary wave solution due to the presence of a small dispersive radiation that propagates to the left due to the non-integrability of the Schamel equation. So we can see the reduction in the amplitude of the second soliton. It was 1.8 and now it's 1.799, yeah, after the interaction. But these changes are minimal. After the collision, the solitary waves have phase shifts. It is clearly seen on the spatial temporal diagram. At any given time, there exist two local maxima, indicating that the wave crests of the two solitary waves never intersect. As a result, this collision can be characterized as highly elastic, with the waves exhibiting a remarkable ability to return their fundamental characteristics during the interaction. Next, the overtaking interaction is when the first solitary wave is significantly larger than the second one. So two solitary waves merge to form a single local maximum for a certain period of time, and a diminutive dispersive tail emerges immediately following the collision of the solitons. We can see again a negligible loss of amplitude of the smallest soliton. Here again we can see the spatial temporal diagram of the collision, the number of local maxima as a function of time, which follows the rule 1 to 1, and the maximum amplitude as a function of time. And finally, the collision of transition type, when the number of local maxima follows a pattern 2, 1, 2, 1, 2 during the collision. And again, we can see a small decrease in amplitude of the second soliton after the interaction, and dispersion radiation produced during the soliton collision. After considering these three types of two soliton interaction, we can say that in spite of the tiny radiation that occurs as a result of the interaction of two solitons, the KdV ideology is also valid for the non-integrable Schamel equation. However, the situation is slightly different with phase shifts. The formula for phase shifts remains the same for both KdV and mKdV equations when formulated in terms of soliton speed c. It is positive for the larger soliton and negative for the smaller one. Formally, no theory currently exists for the Schamel equation due to its non-integrability. However, we conducted a comparison between the analytical phase shifts and the numerically calculated shifts using spatial temporal diagrams in the case of three considered soliton interactions. So the negative phase shifts of the smallest solitary waves in both numerical and analytical calculations ranged from 1.5 to 11%. For larger solitary waves, the difference is from 8 to even 23%. So, as a result, the analytical formula can be used only for some rough estimations in the Schamel equation. To study the impact of two soliton interaction into statistical characteristics, we evaluate the following moments. While the first two integrals remain constant over time, representing the mean and variance of the system, the higher order moments, such as third and fourth moments, reduce during the interaction, as in case of KdV. It can be explained by the decreasing of the amplitudes of solitons during the interaction. And now let us consider the features of bipolar soliton interaction within the Schamel equation and compare it with the interaction of MKDV solitons, which also may be positive and negative. Again, we set the initial wave field as a linear superposition of two solitons. First, amplitudes of solitons are close enough by modulus. So before interaction, the value of maximum wave field is equal to the value of the amplitude of the largest soliton, which is 1 here. At the moment of interaction, it increases up to the value equals to 1.53. However, after the separation, it doesn't return to its original value and remains at the level of 1.09. This means that a positive soliton increases its energy after the soliton collision. Consequently, the negative soliton loses its energy. In comparison with the integrable MKDV case, it is an inelastic collision with energy transfer from smaller to larger soliton. Another finding is that the angle formed with the positive axis OX and the soliton trajectory changes after the collision. There is a big difference in comparison with the MKDV case, where only phase shift occurs after the collision and the trajectories have the same angle. Here, soliton amplitudes differ more. The value of the maximum wave field almost returns to its original value, and the angle between the positive axis OX and the soliton trajectory does not change after the collisions. As you can see, the feature of soliton interactions depends a lot on the amplitudes of the solitons. And the effect of energy transfer is especially significant in case of close amplitudes. Let us consider the qualitative differences between the interaction of bipolar solitons within the non-integrable Schamel equation and integrable modified Korteweg-de equation. The differences in shapes and velocities of solitons contribute to the difference in the interaction processes. Here is the process of two soliton interactions within the MKDV model in red and Schamel equation in blue for close amplitudes of the solitons. The interaction of bipolar solitons leads to an increase in the amplitude of the resultant impulse. However, within the MKDV model, the resultant amplitude presents the linear superposition of the modulus of amplitude of the initial solitons. In the framework of the Schamel equation, when solitons have closed amplitudes by modulus, the scenario, on the one hand, is less extreme than the MKDV case, because the resultant impulse is less than in the MKDV case. On the other hand, the amplitude of the largest soliton increases after the interaction. This may lead to the consumption of the energy of the largest soliton in soliton gas, and as a result, it may be considered as a new mechanism of a freak wave formation due to the non-integrable effects. When the initial amplitudes of the solitons significantly differ from each other, the resulting impulse in the Schamel equation is again less than in the MKDV case, but not significantly, because the non-integrable radiation is small in this case. The third and fourth moments increase in the moment of soliton interactions due to the increase in the amplitude of the resultant impulse. The peaks of the moments are predictably higher within the MKDV equation than in the Schamel equation because the growth of impulses is larger in the case of MKDV equation. By analogy with the maximum of the wave field in the integrable MKDV equation, due to elastic soliton interaction, the values of the third and fourth moments before and after the interaction are identical. Within the Schamel equation, the value of the moments after the interaction becomes bigger than before the interaction, especially for close amplitudes. Now let us move to multi-soliton interaction, so-called Soliton turbulence of soliton gas. First, our wave field consists only of unipolar solitons, so solitons with the same polarity. We set initial wave field as a sequence of 100 separated solitons with random amplitude uniformly distributed from the range of 1 to 3 in random order, and fixed distance between the positions is 20 units. The solitons propagate to the right and, owing to different speeds, interact with each other. It is well known that interaction of unipolar KdV-like solitons leads to a decrease in amplitude of resulting impulse. In the non-integrable Schamel equation, this property is the same in case of two soliton collisions. However, there is a radiation created by inelastic collisions of solitons, which is displayed in details in the bottom figure. Here, the amplitude of the biggest initial soliton is 3, and in the figure, maximum of the wave field reaches 3.07. The fluctuations of the wave fields, which form after soliton collisions, are small enough in order to influence high statistical moments, skewness and kurtosis. Figures at the top demonstrate the temporal evolution of skewness and kurtosis of the unipolar soliton field for one realization, painted with blue, and averaged value over 20 realizations, painted with red. Similar to KdV model, there is a short transition zone of sharp decrease of moments till about time equal to 50. And it is the same for all realizations of soliton gas. Averaging over realizations predictably diminishes the fluctuations of moments, and it tends to stationary state. The average distribution function of wave amplitudes undergoes a downward shift in the high amplitude region. Consequently, the presence of large waves diminishes, leading to a more uniform wave field. These findings align with similar observations made in studies involving soliton gases governed by the KdV and MKdV equations. A presence of solitons with different polarity makes the dynamics of the wave system more extreme. Again, we set initial wave field as a superposition of separated positive and negative solitons, and we set these solitons to have random amplitudes uniformly distributed in the range from 1 to 3 and from -1 to -3. There is an example of the initial soliton gas. Solitons interact with each other over time, and there are collisions of big number of solitons. It may contribute to significant growth of the wave field. Thus, in considered realizations, the maximum wave field reached almost 7, as we can see here. And the wave field, which contains the freak waves, is presented on the top figure. And the more details of its formation is depicted in the bottom figure. In the process of nonlinear interaction, skewness changes quite much in one realization, the blue line, but the ensemble of bipolar solitons is close to be symmetrical, and the average value of this statistical moment is around 0. Skewness takes both positive and negative values depending on the prevalence of positive and negative solitons. This figure demonstrates the gradual growth of the averaged value of kurtosis. It may be explained by increasing of number of small amplitude waves. Thus, large waves become more extreme. This behavior of kurtosis differs from the KdV model, where averaged kurtosis reached the steady state. The increase in kurtosis indicates the amplification of the distribution function tails. And here are the conclusions. So first of all, the interactions of two unipolar solitons within the non-integrable Schamel equation are close to the interactions within the integrable KdV and mKdV equations, except maybe the phase shift. Bipolar soliton interactions lead to the freak wave formation, as in mKdV case, and inelastic interactions of bipolar solitons within the Schamel equation lead to the transfer of energy from the smaller soliton to the larger one. It leads to a significant increase in kurtosis, which would remain constant in integrable systems. And the results obtained here were published in these three articles. Thank you for your attention.